Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the Navier-Stocks equations and its derivations. So, we have seen for viscous flows, we have to consider the viscous effects and then using the Newton's second law of motion. We have seen how we derive the Cauchy's equation first for any kind of viscous flows, and then from the Cauchy's equation we have derived the Navier-Stokes equations for 2 dimensions, and then we have seen how to extend these 2 dimensional equations to the 3 dimensions. So, in this Navier-Stokes equations we have seen in this the formulation with the velocities and pressure. So, we have in 3 dimensions we have say u, v, w, 3 velocity components as unknowns, and then p the pressure unknown. So, we have 3 equations of motions called the Navier-Stokes equations, and then we have the continuity equation in 3D. So, 4 equations and 4 unknowns, and then to find out the velocity distribution or pressure distribution, we have to solve this equation by using the appropriate initial conditions and boundary conditions. So, here you can see that say now this equation is second order and nonlinear in nature. So, to get an exact solution it is very difficult. Only for few simplified cases only we can have the exact solutions. So, most of the time for practical problems we cannot get an exact solution. So, we have to solve this second order nonlinear differential equation, partial differential equation, generally using numerical methods. So, here these are the equations in 3D. We have 3 equations of motions called Navier-Stokes equation and the continuity equation. So, here we assume that the density and the coefficient of viscosity mu are known, and then we try to solve this equation. So, as we have seen as we discussed earlier, this Navier-Stokes equations are the generalized equation for viscous flows. So, these equations we can use for most of the fluid flow problems with appropriate modifications. We can use for laminar flow, we can use for turbulent flow, we can even use for compressible flow with appropriate changes. This is the advantage of Navier-Stokes equation. Once we we make a model for the Navier-Stokes equation that can be applied for various cases of fluid flow. So, and then but say generally we use this Navier-Stokes equations, our assumption is in such a way that these equations are applicable for Newtonian fluids. So, non-Newtonian fluids we cannot utilize these Navier-Stokes equations. So, with the given equations for the given problem we have to supplement with the initial and boundary conditions. So, here as you can see for a 2D problem, so the initial conditions can be, so either velocity or pressure, the distribution will be known throughout the domain, and then the boundary conditions we can supply either in terms of the generally in terms of velocities or in terms of say depending upon the pressure or other parameters. So, here this particular say if you consider 2-dimensional problem, say for a typical case we can say that here if this velocity u component is equal to 1, v is equal to 0, here u is equal to 0, v is equal to 0, and here the flux del u by del n is equal to 0, del u by del n is equal to 0. Like that we can supplement the problem with the appropriate boundary conditions. So, similar way if you consider a 3-dimensional problems, so with respect to x, y and z. So, say if we consider the flow in a cubic cavity like this. So, here we can just use the Navier-Stokes equation with appropriate boundary conditions. Say for example, if you consider the incompressible viscous flow in this cavity, say let us assume that this lid is moving with a velocity u is equal to 1, and then v and other w are 0. So, all other sides also u, v, w equal to 0. So, this can be a typical cubic cavity problems which is generally used to develop the computer codes using Navier-Stokes equation and then for verification purpose. So, here the boundary conditions are u, v, w are 0 on all these sides, and on the top lid u is equal to 1 and v is equal to 0, w is equal to 0, and the initial conditions we assume either the velocity as 0 or if the known values the velocities are known, then initial conditions are given to solve this this partial differential equations or the Navier-Stocks equation. So, all the problems once the governing equations, say either as the form which we discussed here or any other forms, say different forms like we have already seen in the case of turbulent flow, the Navier-Stocks equation will be in some other different format by considering the turbulent components, velocity fluctuating components, or say some other formulations like say we can use the vorticity stream function formulation, like that. Different kinds of formulations are available for different problems. So, accordingly we will be supplying the initial conditions and the boundary conditions to solve the particular problem which we consider. So, this way, so once the domain is defined, we depending upon the problem we decide which form of the Navier-Stocks equation will be used, and then continuity equation will be used, and then we will be using, if exact solutions are not possible, we will be using some approximate or numerical methods to solve the equations by using appropriate initial conditions and boundary conditions. So, now some other aspects of these equations which we consider here, the initial conditions and boundary conditions can be generally in terms of u, v, w, that means the velocity component and pressure. So, either velocity or pressure depending upon the problems. So, as we have already seen, and then generally whenever the solid boundaries are there, so here we consider the viscous flow. So, no slip condition is used wherever the solid boundaries are there, and then as we have seen, this Navier-Stocks equation non-linear differential equation second order. So, exact solutions extremely difficult other than simple cases. So, depending upon the problem, so either turbulence is involved or say the problem is it even the compressible, it can be also approximated with respect to change in the, we can change the equation in such a way that compressibility effect also can be considered. So, depending upon the problem, say which way we consider or which way we have to solve the problem may become more complex. So, exact solutions extremely difficult other than the simple problems. So, now here this Navier-Stocks equations which we have already derived in earlier. So, here we can write in vector form as del v by del t plus v dot del v is equal to g minus 1 by rho del p plus nu del square v. So, where nu is the kinematic viscosity, v is the velocity vector, and p is the pressure, rho is the density, and g is the acceleration due to gravity. So, here this Navier-Stocks equation is written in vector form, and if we analyze here, we can see that each of this term is actually acceleration term. So, the acceleration term, you can see that the unit is length divided by time square L or L by t square. So, depending upon the, say, each term represents an acceleration term. So, here you can see in the equation the first term. So, if we consider del v by del t, so here it is the change in velocity with respect to time, that means acceleration, local acceleration del v by del t. So, it is local acceleration. So, local acceleration of the fluid particle at a fixed point in space. So, for steady state flow, if we consider steady state flow, this del v by del t term will be 0. So, otherwise we have to consider del v by del t. So, this term is called a local acceleration term. And then the second term here, this v dot del v. So, this term is actually the convective acceleration of the fluid particle. So, it predicts how the flow differs from one point to next at the same instant of time. So, we can see that when the fluid is flowing, say from one place to another depending upon the pressure difference, we can see that there is say the local acceleration as we have already seen, then the convective acceleration. So, the velocity of the flow also say takes the flow to one place to another. So, it is called convective acceleration. So, this convective acceleration, it is say this term as we have seen, this second term. So, it gives how the flow differs from one point to the next at the same, say if we consider at a particular time. So, from one point to another how the flow takes place. So, that is what this convective acceleration gives. And then the third term, so that means g or the body force. So, the force due to the gravity, or this shows how the effect of the acceleration due to gravity or gravity effects on the body, and it is generally represented as body force. So, this term C represent the acceleration due to gravity, and term D that means minus 1 by rho del P in the previous equation. So, here this term 1 minus 1 by rho del P. So, this represent the pressure acceleration. So, even that also we can represent, say, as a pressure acceleration due to, say, pumping action of the flow. So, that gives the pressure variation term. And then the next term, so here the last term nu del square V. So, that gives this term term E, or fifth term nu del square V gives the viscous deceleration due to fluid frictional resistance to objects moving through it. So, here we consider the viscous flow. So, for the viscous flow there is always resistance for the flow. So, this term gives the nu del square V gives the deceleration. So, actually due to the viscous effect there is effectively deceleration takes place. So, this term gives the viscous deceleration due to the fluid frictional resistance to objects moving through it. So, like this we can see that here in the Navier-Stocks equation, when we write the vectorial here, the vector form, when we write, we can see each term we can represent as an acceleration or deceleration term depending upon the case which we consider. So, now before further discussing how to solve or how to get some solution for this equation, so we will see each few of the terms, the significance of some of the terms. So, here as we have seen the significance of body force. So, the body force we have already seen, this is due to gravity. So, this is important for flow problems with the free liquid surface or liquids in non-homogeneous or with a density gradient. So, if you consider any flow with say free surface, say for example, a flow is taking place on a plate is inclined, plate is like this, and then if you consider a free surface flow over this plate, you can see that the acceleration due to gravity effect is there for this. So, here this plate is inclined at an angle theta. So, G component is acting here, and then for this, say the body force is predominant here. So, we have to consider this body force. So, this is due to gravity, and it is very important, and also sometimes if non-homogeneous density, that means the fluid is non-homogeneous. So, if there is density gradient exists, in that case we have to consider the body force. So, also say in case if there is any rotating fluid, so you can see that many times we have to consider, say especially in mechanical engineering, there is a number of machines parts with the fluids will be rotating, and then if you consider the rotating fluid, then the body force due to centrifugal force action also to be considered. So, here you can see in this slide, you can see rotating fluid. So, in this case we have to consider the centrifugal action, that is on the body force with respect to centrifugal action. Also we have to consider this kinds of problem. And then second, say the other important term is the viscous term. So, we have already seen now the Navier-Stocks equation which we have derived is for viscous flow. Viscous term, say when the viscosity increases, we can see that there is more resistance to flow. So, depending upon the fluid which we consider, so there can be the viscosity will be changing. So, viscous fluid different with the ideal fluid, so or the potential flow which we consider in viscous or friction terms, and then the equation we have seen the second order or second derivatives of viscous terms. So, depending upon the fluid, if it is more viscous, then this effect will be much higher, and then there will be more resistance to the flow, and hence deceleration takes place. So, depending upon the fluid which we consider the Navier-Stocks equation. And say now, before further going to the solution of some of this say the especially exact solution for the few cases of the Navier-Stocks equation. We will consider some of the limiting cases. So, Navier-Stocks equation which we consider here. So, the viscous forces tends to 0, then you can see, as we have seen, the viscous force is tending to 0, that means the viscous effect nullified, or it is very less. Then we can consider the flow as potential flow. So, that this that second order nu into del square u or del square v or del square w, that term we can neglect depending upon the problem. And then second case is viscous force are of higher order magnitude, and that means in this case. So, the second limiting case here, the viscous force are of higher order of magnitude and lower Reynolds number. So, here we say that this is creep flow. So, here the Reynolds number is so low and viscous force are of higher order magnitude. So, it is the say very the fluid velocity is very less, and we call such kinds of flows creep flow, or sometimes also Stokes flow. We will be considering, we will be discussing more detail on the creep flow later. So, here this is another second limiting case where the viscous forces are higher order of magnitude. And third case is non-zero viscous forces, but of smaller magnitude than inertial forces. So, here the especially the aerodynamics flow problems which we consider, the Reynolds number will be so high, so that we can say that non-zero viscous forces, but of smaller magnitude than the inertial forces. So, these are some of the limiting cases where we consider the Navier-Stocks equations. So, depending upon the case, as I mentioned earlier, so we have to modify the equation, Navier-Stocks equations, and then we have to try to get a solution. Then, as far as potential flow is concerned, so let us consider the non-viscous fluid, say as in the case of potential flow theory. So, for potential flow problems, we have already seen that the velocity components u, v, w can be expressed as u is equal to, phi is the potential, velocity potential. So, u is equal to minus del phi by del x, and v is equal to minus del phi by del y, and w is equal to minus del phi by del z. So, that we can also write, so for irrotational potential flow irrotational case, we can write del square phi by del x square plus del square phi by del y square plus del square phi by del z square is equal to 0. So, now also by using the continuity equation at steady state, we can write this nu into del square u can be written as nu del square u by del x square plus del square u by del y square plus del square u by del z square. And then if we use this here, substituting for u v w and then interchanging the differentiation parameter here. So, we can write nu into del square u is equal to minus nu del by del x of del square phi by del x square plus del square phi by del y square plus del square phi by del z square. So, this term we have here for irrotational flow and potential flow, this term is 0. So, we can show that nu into del square u is equal to 0. So, for non-viscous flow, especially with respect to the potential flow theory, at steady state we can see that the viscous terms of the Navier-Stocks equation in terms of velocity potential, once it is written, we can show this nu del square u is equal to 0. So, similar way, the second the y direction as well as z direction, we can show that nu del square v is equal to 0 and nu del square w is equal to 0. So, that means for potential flow, the potential flow is characterized by the velocity potential, and viscous terms in the Navier-Stocks equation are identically 0. So, that means we can see that here, if we consider the potential flow, then the Navier-Stocks equations are reduced to Euler's equations which we considered earlier. So, for potential flow, say we have already shown that the viscous terms nu del square u and nu del square v and nu del square w are zeros, and finally, the Navier-Stokes equations are transformed into the Euler's equation. So, potential flow, the Navier-Stokes equation becomes Euler's equations, and we can solve the Euler's equation. And then for inviscid flow, that means in the case of ideal fluids flow, Navier-Stocks equation, which we have already seen here, the Euler's equation for say the general form of the equation is del V by del T plus V dot V is equal to G minus 1 by rho del P. So, this form of the equation we have already seen the Euler's equation. So, del V by del T plus V dot del V is equal to G minus 1 by rho del P. So, this is the Euler's equation. So, here we have already in the previous slide we have already shown that these terms, the viscous terms become 0 for potential flow, and then we get the Euler's equation. So, and also flow at very large Reynolds number, example aerodynamics problems, viscous forces are much smaller than the inertial forces, and viscous terms in the Navier-Stocks equation can be dropped. So, for high Reynolds number flow also we can drop the viscous terms, since the viscous forces are much smaller than the inertial forces. So, that we can drop the viscous terms. And Navier-Stocks equations reduce equations for non-viscous fluid. So, we can say in the case of the aerodynamics problems, when we consider the high Reynolds number flow, we can show that the viscous terms we can drop, and then say if we model using the say the case without the viscous terms, that will be also a good approximations, but away from the boundary, but near the boundary of course the effects will be there. So, for example, if we consider here say a fluid, say let us consider a cylinder like this, and then flow is coming in this direction. So, you can see that away from the, so here nearby the cylinder there will be definitely the effect, the boundary layer effects will be there, but away from the cylinder you can see that there will not be much effect for this, say, but near the boundary we have to consider the boundary layer. So, while solving these kinds of problems we can say consider, so the now if you consider the flow over a cylinder like this, we can consider the nearby area, say we can consider like this nearby area we may have to solve the Navier-Stocks equation, but far say away from the solid boundary. So, we can consider away from the boundary we can solve this here the Euler's equation, or even the simple potential flow we can use this area, but near to the solid boundary we have to consider, since viscous effects will definitely will be there and the boundary layer formation takes place. So, in this region we can directly solve the Navier-Stocks equations, and say further away from the boundary this region we can consider as potential flow as an approximation. So, this solve this gives a better approximation than, especially when we solve very large scale problems, this gives a lot of advantage, since we can restrict our the solution of the Navier-Stocks equation near to the boundary, and then away from the boundary we can consider the flow as potential flow. So, for the cases wherever the say of higher Reynolds number, then we can see that a good approximation is away from the boundary we can consider, we can drop the viscous terms, and near the boundary the solid which we consider, there we will be solving the Navier-Stocks equation. And then as we have already seen, for very slow fluid motion called Stokes flow or creep flow, when say in the case of unsteady or transient condition, we can write the equation as del U by del T is equal to x minus 1 by rho del P by del x plus nu del square U. So, if we consider the equation in x direction, where capital X is the body force, and at steady state, so and if there is no body force, then we can write this equation as del P is equal to mu del square V, where V is the velocity component, the velocity vector which we consider, and P is the pressure. So, for very slow fluid motion, like in the case of say these equations are very much useful in the case of lubrication mechanics, and then also capillary flow, and also molten metals, especially metallurgy, wherever we consider the molten metals also we can utilize this form of the Navier-Stocks equations. So, we have now seen three limiting cases. One is the creeping flow or the Stokes flow, where the viscosity is so high that we will be considering the equation as say without the viscous the effect is much higher, and then we consider the last case here we considered, and then the other case is the potential flow, where we consider the viscous terms can be neglected, and then we can transform the case to the Euler's equation. And then third case is wherever the say problems like aerodynamics problem, where the higher Reynolds number case is there also as a limiting case, the effect of the viscous terms sometimes we can say far away from the solid surface we can neglect, since that effect will not be much, of the viscous effect will not be much. So, these are some of the limiting cases where we consider the Navier-Stokes equations. And now, say the Navier-Stokes equations which we derived are in the Cartesian coordinates. So, certain problems like flow through pipes or say rotating fluid cases, then if we consider cylindrical coordinates in terms of r, theta and z, so then the equations, the Navier-Stokes equation we can derive for that kinds of problems, say for example either a pipe flow like this, so where r is the radius and theta is the angle and z is this direction. So, r theta z. So, here the coordinate systems are in terms of r theta z instead of x, y and z. So, the velocity components correspondingly, the velocity components are Vr, V theta and Vz. So, these equations, what we have seen, the Cartesian coordinates equation we can transform into the cylindrical coordinate in terms of r theta z and the corresponding velocity Vr, V theta z. So, here we are not going for the derivation, but the equations here are written directly. So, the radial component r component is del Vr by del t plus Vr del Vr by del r plus V theta by r del Vr by del theta minus V theta square by r plus Vz del Vr by del z is equal to Gr minus 1 by rho del P by del R plus nu into del square Vr by del R square plus 1 by R del Vr by del R minus Vr R by R square plus 1 by R square del square Vr by del theta square minus 2 by R square del V theta by del theta plus del square Vr by del Z square. So, this is the radial component in cylindrical coordinates. So, here Vr is the radial velocity, V theta is the tangential velocity and Vz is the axial velocity, and r is the radius which we consider, rho is the density, Gr is the acceleration due to gravity in the radial direction. So, this gives the radial component of the Navier-Stokes equation. And then the tangential component, theta component can be written like this: del V theta by del t plus Vr in del V theta by del r plus V theta by r in del V theta by del theta plus Vr into V theta by r plus Vz in del V theta by del z is equal to G theta minus 1 by rho r del P by del theta plus nu into del square V theta by del r square plus 1 by r del V theta by del r minus V theta by r square plus 1 by r square del square V theta by del theta square plus 2 by r square del Vr by del theta plus del square V theta by del Z square. So, here nu is the kinematic viscosity and G theta is the acceleration in the direction of the theta component, and Z component, the third component for the Navier-Stokes equation can be written as del Vz by del t plus Vr into del Vz by del r plus V theta by r del Vz by del theta plus Vz del Vz by del Z is equal to Gz minus 1 by rho del P by del Z plus nu into del square Vz by del R square plus 1 by R del Vz by del R plus 1 by R square del square Vz by del theta square plus del square Vz by del Z square. So, this is the Z component. So, this the cylindrical coordinate system the Navier-Stocks equation which we considered, say we can apply in the case of wherever r theta and z and Vr V theta Vz components are problems of the, say like rotating fluids are considered, it will be better to use this cylindrical coordinates equation than the Cartesian coordinate equation which we have seen. So, now before going for the exact solution, few of the exact solutions and numerical solution of the Navier-Stocks equation, the applications of Navier-Stocks equation. So, as I mentioned earlier, so this Navier-Stocks equation was the say some of the fundamental equation of the fluid mechanics, basic partial differential equations as far as viscous fluid flow is concerned. So, these equations, say these are written especially for Newtonian fluids. So, we can apply for most of the problems including turbulence flow, laminar flow or compressible or incompressible fluid, all the varieties we can modify the equation and get the appropriate equation depending upon the problem which we consider. So, exact solutions, so as far as solutions are concerned, exact solutions for these equations are extremely difficult. Only simplified cases, say especially in one dimension or two dimensions, and then also steady state conditions, we can have some simple analytical or exact solutions, but otherwise since second order nonlinear partial differential equations we cannot get exact solutions, and most of the practical problems are also the boundary conditions will be complex and the geometry will be complex. So, for the most of the practical problems we cannot get any exact solutions, we have to go for numerical solutions. So, exact solutions of Navier-Stokes equation is only possible if convective terms are absent, but as I mentioned, for most of the practical problems, say the exact solution we cannot derive exact solutions, but for simplified boundaries and simple cases wherever the convective terms are absent, we can derive some of the exact solutions. So, here we will be say discussing few of the exact solutions before we discuss briefly on the numerical solutions for the Navier-Stokes equations. So, as far as exact solutions are concerned, say the solutions are exact, so that the equations are satisfied at every point of the flow domain. So, if we consider the flow in a cubic cavity or any kind of flow, so the exact solution, if you derive that solution should satisfy throughout the domain. So, say the exact solutions we can generally write, it can be in terms of velocity. So, we can write u as a function of u x t, this x represent the coordinate system x y z corresponding to 2D or 3D or 1D problem, and p is in terms of p x t. So, that means spatial and time coordinates as far as we get the velocity variations and the pressure variations in terms of the spatial and time coordinates. So, generally say whatever the analytical solution derived so far are basically the analytical solution uses generally two approximations. One is flow is fully developed. So, see most of the analytical solutions which are derived in literature are for fully developed flow, and then the Reynolds number is quite small. Only say if the Reynolds number is large, then it is extremely difficult to derive any of the analytical solutions. So, generally in literature the analytical solution which are available are for fully developed flow, and the Reynolds number is for the flow, the Reynolds number is small. So, here we will be discussing few of the analytical solution or exact solutions. So, some of the exact solutions or analytical solution possible for the Navier-Stokes equations are listed here. First one is laminar flow between fixed parallel plates, and this we will be discussing in detail. And next one is Q-tape flow, then steady incompressible laminar flow in circular tubes, axial flow in annular space between two fixed concentric cylinders, and then other cases like wherever the flow of two immiscible fluids in channel steady state conditions. So, these are some of the cases where we can derive the exact solutions for the Navier-Stocks equation which we have seen. So, in all these cases we assume that the flow is fully developed, and then Reynolds number is so low that we can consider the flow as laminar. So, few of these exact solutions here we will be discussing in detail. So, first case which we want to discuss here is called a plain Poiseuille flow. So, here the plain Poiseuille flow is, say, what we consider is the flow between the flow through two parallel straight channels placed at a distance, and flow is the parallel flow through between these two plates. So, here you can see two plates are placed at a distance of 2t, and here we consider the axis in this direction. So, we consider here the flow as steady state, and then flow is one dimensional. So, since steady state means, now to get an exact solution, generally what we do is, so we know the generalized Navier-Stocks equations. So, depending upon the problem, so we derive the we use the various assumptions and various simplifications which we use for that particular problem for which we are trying to derive the exact solution. So, here in this particular case we assume that flow is fully developed, and then the flow is steady state. So, steady state means this del by del t is equal to 0, and here this particular case actually it is one dimensional flow. So, we can see that V is equal to W is equal to 0. So, now since V is equal to 0, W is equal to 0, so that we can see that from the continuity equation we can write del U by del X is equal to del V by del Y is equal to 0. So, now the pressure variation P is a function of x and y, and then we can see that now the U is varying only in the direction of y. So, U is a function of y, and also we can see this particular case del P by del Y is equal to 0 as V is equal to 0. So, the pressure is varying with respect to x, and then velocity is varying with respect to y. So, finally, now with respect to these assumptions, so here the assumptions for this plain Poiseuille flow are, it is flow is steady state, flow is one dimensions, and parallel flow. So, now by using all these assumptions we can simplify the Navier-Stocks equations which we have seen earlier as a single equation as del P by del X is equal to mu del square U by del Y square as in equation number 1. So, after putting this all the simplification, finally we get del P by del X is equal to mu del square U by del Y square. So, now we got the governing partial differential equation. So, our aim here is to get the velocity variation or the pressure variations as we have discussed earlier. So, now the boundary conditions, since here no initial conditions, since we consider the flow steady state. So, the boundary conditions here what we are using are, so the no slip condition, that means with respect to this figure on the wherever the flow is, say here on the plate, that means on this location and on this location, say at y is equal to plus t and y is equal to minus t, we can see that the velocity is 0. So, that actually the velocity variation will be parabolic like this. So, the boundary conditions are at y is equal to plus t, ux is equal to 0, at y is equal to minus t, ux is equal to 0. So, now we got the equations here. So, what we can do, our aim is to get an expression for the velocity variation. So, now the equation which we got is mu del square U by del Y square is equal to del P by del X. So, the velocity is a second order differential equation what we got. So, here to find the velocity we can integrate twice this equation, and then we can apply the boundary condition. So, if you integrate twice, we get ux is equal to 1 by 2 mu del P by del X y square plus C1 y plus C2. So, this is the expression for the velocity. So, now the C1, C2 are the constant. So, we can apply the boundary conditions. So, we have got two boundary conditions here at t is equal to t, velocity u x is equal to 0, at t is equal to minus t also velocity u x is equal to 0. So, we can use these boundary conditions, so that we can see C1 is equal to 0 and C2 is equal to minus 1 by mu dp by dx into t square by 2. So, now we can substitute for this C1 and C2 in this equation. So, that the expression for velocity is obtained as u x is equal to 1 by 2 mu dp by dx into y square minus t square. And then if you want to find out the maximum velocity, so in this particular case the maximum velocity occurs at the center line. So, at y is equal to 0, the maximum velocity u max is equal to minus 1 by 2 mu dp by dx into t square. This gives the maximum velocity. And then if you want to find out the average velocity, u average is equal to 1 by 2 t. We can integrate between the limits minus t to t u dy. So, this will be equal to 2/3 of the maximum velocity. So, the average velocity for this case is 2/3 of the maximum velocity. So, like this, so this is a typical problem, the plane Poisson problem, where the flow is between two parallel plates, two fixed parallel plates, and then as we have seen, we use the various assumptions for this typical problem, and then we simplify the general Navier-Stocks equations, and then to get an expression for either velocity or pressure, the unknown parameters, we use the simplified form of the Navier-Stocks equation, and then integrate to get the velocity. Here we have integrated twice to get an expression for the velocity, and then we use the boundary conditions to obtain the expression for velocity. So, this is the way which where we consider the Navier-Stocks equation to get some of the analytical solutions or exact solutions. So, the case which we have seen is the plane Poisson flow problem. So, for this typical problem, so here are two fixed plates and the flow is between, then you can see that the flow develops for the fully developed flow, the flow develops like this, and the entrance is here, and the flow, you can see that the flow develops like this. So, the velocity vectors are plotted here. So, the maximum velocity is here and the velocity develops in this pattern. So, this is the case of flow between parallel plates we have analyzed using the Navier-Stocks equations. And now, the second case, so what we have seen is the flow between two fixed parallel plates. The second case what we consider here is called Q-tape flow, the plane Q-tape flow. So, here in this case, the second case, so the out of the two plates, one plate is bottom, this plate bottom plate is fixed and the top plate is moving with a velocity u. Say for example, this, if you consider here, this is this two parallel fixed plate. So, the bottom plate is fixed and the top plate is moving like this. So, with a velocity u. So, here the Navier-Stocks equation. So, now the almost all the assumptions which we used earlier are valid here also. So, only difference is that the top plate is moving with a velocity u. So, here we consider the distance between the plates as t. So, the distance between the plates is t. So, this the velocity with which the top plate is moving is u. So, the Navier-Stocks equation becomes dp by dx is equal to mu into d square ux by dy square as in equation number 1. And here the difference between the Poisson flow, plane Poisson flow which we have seen is here the top plate is moving. So, the boundary conditions changes. So, the boundary conditions which are used here. So, for this case where the plates are at a distance t. So, at y is equal to 0, that means bottom, here the bottom plate is fixed. So, that the velocity is equal to 0. So, ux is equal to 0 and then the top plate is moving with a velocity u. So, at y is equal to t, u is equal to ux. So, these are the boundary conditions. So, in a very similar way as we have seen for the plane Poisson flow, here also we can integrate this expression, the Navier-Stocks, the simplified form of the Navier-Stocks equation twice to get an expression for velocity. So, we can write ux is equal to, if we integrate twice, we get the velocity ux is equal to 1 by 2 mu dp by dx y square plus c1 y plus c2. So, where c1 and c2 are the constants of integration. So, now we have two boundary conditions here, ux equal to 0 at y is equal to 0 and y is equal to t, ux equal to u. So, we can use these two boundary conditions to get the unknown c1 and c2. So, c2, by using the boundary conditions, here we can see c2 is equal to 0 and we get c1 is equal to u by t minus 1 by 2 mu dp by dx into t. So, where t is the distance between these two plates. So, we get c1 is equal to u by t minus 1 by 2 mu dp by dx into t. So, now we can substitute this c2 and c1 in the equation for velocity. So, we get ux is equal to y by t into u plus y by 2 mu dp by dx into y minus t. So, this is the expression for velocity. So, if dp by dx, in this particular case, if dp by dx is equal to 0, we get a so called shear flow, where we can just write ux is equal to u into y by t. So, this typical case where the pressure gradient is 0 is called a shear flow. This is a special case of this. So, here this Q-tape flow, which we considered, has got number of applications. So, depending upon the problem, so for this Q-tape flow, you can see that we can have various cases. So, the case, say we have already seen the plane Poisson flow, both the plates are fixed. So, some cases, another typical case is say both plates will be moving in opposite directions. Say for example, if we consider the two plates like this. So, what we consider the plane Poisson flow is both the plates are fixed, and then Q-tape flow we consider one plate is moving like this, and then another case which we consider is say both plates are moving in opposite direction like this. So, this is another case which we can consider, both plates are moving in opposite direction. So, here again the assumptions are same, and then the only boundary conditions, say the top plate will be having one velocity in one direction and the bottom plate will be having another velocity in the opposite direction. So, depending upon the case, then here for various cases the velocities are plotted. So, here if you consider this plate is moving, top plate is moving with a velocity u and velocity bottom plate is moving the opposite direction with the velocity, then we may get, depending upon the case, the velocity variation like this, and then say the bottom plate is fixed and the top plate is moving with a velocity 2 times of say 2 ux, then you can see the velocity variation can be like this. So, this is the case where the plane Poisson flow, where both plates are fixed, and then if the bottom plate is moving like this, then the velocity variation can be like this. So, depending upon the problem, so this the case which we considered, either it can be plane Poisson flow or Q-tape flow, or the both plates moving in the opposite direction. So, these are the various cases. So, now we will consider another case where we can have an exact solution. So, it is called a suddenly accelerated plane one. So, here the Q-tape flow and plane Poisson flow, which we considered earlier, we considered the flow as the steady state. So, here we consider a case where unsteady problem. So, here the problem statement is like this. So, the plate is here, a flat plate suddenly accelerated from rest and it moves in its own plane with a constant velocity u0. So, here a plate is placed in a fluid, and then the plate is suddenly accelerated from rest and it moves in its own plane with a constant velocity u0. So, this is the problem. So, compared to earlier case which we discussed, so here the change is from the rest, the plate is suddenly moving with a velocity u0. So, this is an unsteady problem. So, for this typical case, we can write the governing the Navier-Stocks equation can be transformed and written like this: del ux by del t is equal to nu into del square ux by del y square. So, where nu is the kinematic viscosity. This gives for this typical problem, this is the transformed form of the Navier-Stocks equation. So, this equation is actually the diffusion equation or heat conduction equation, this form of the equation. So, equations in y and z need not be considered at all because of the unilateral motion of the plate. So, here we consider the equation only, the plate is moving only in this direction in the fluid. So, we do not have to consider the y and z component, and the Navier-Stocks equation is in this the form of equation number 1 here. So, now we have to derive an analytical solution. We are trying to derive an analytical solution with respect to the simplified form of this the unsteady case of this typical problem. So, here the boundary conditions are for t is less than or equal to 0, that means before the time start. So, that means t is equal to 0, ux is equal to 0 since plate is at rest. So, everywhere, and also initial condition also in the velocity component ux is equal to 0, and for t greater than 0, that means when this plate is starting to move, t is greater than 0, we can write ux is equal to u0 at y is equal to 0, and for t is greater than 0 and we get ux equal to 0 at y is equal to infinity. That means here this problem, so at a large distance away from the plate, you can see that the velocity will be 0. So, only at this location we have to consider t is greater than 0, ux equal to u0, otherwise at a large, at a infinity, at a large distance at y is equal to infinity, ux equal to 0. So, now we use these boundary conditions to derive a solution for this problem. So, now this problem is, you can see that here two parameters, the independent variables t and y, and the velocity is ux. So, for this to derive an expression, we will use some say techniques, mathematical techniques here. So, here we introduce a non-dimensional parameter eta, such as eta is equal to y by 2 square root of nu into t, where t here is the time and nu is the kinematic viscosity, and then we can write the velocity variation ux is equal to u0 into a function f eta as in equation number 3. So, that now we can write del ux by del t is equal to del ux del eta into d eta by dt or d eta by dt. So, that we can write u0, this is equal to u0 into df by deta into y by 2 square root nu into minus half into 1 by t to the power 3 by 2. So, hence we can write del ux by del t is equal to minus u0 df by d eta into eta by 2t by using this equation number 2. So, here we are transforming the system in such a way that we are trying to get a solution for this simplified form of the Navier-Stocks equation by using these boundary conditions. So, similarly, we can write del square ux by del y square is equal to d by deta of into u0 df by deta into 1 by 2 square root of nu t into d eta by dy, that is equal to u0 into d square f by d eta square into 1 by 4 nu t. So, we can now substitute for the approximations with respect to this introduction of this eta. We have written for del ux by del t and del square ux by del y square. So, we can put it back in equation number 1. So, we get d square f by d eta square plus 2 eta df by d eta t d eta is equal to 0 as in equation number 4. So, correspondingly the boundary conditions in terms of eta are also we have to change. So, at eta is equal to 0 we get f is equal to 1 and eta is equal to infinity we get f is equal to 0. So, here in this equation, equation number 4, we put df by d eta is equal to p, then we get d square f by d eta square is equal to dp by d eta, and hence integrating this equation number 4 we can write log e p is equal to minus eta square plus log e c, or we can write p is equal to a constant c. So, here this c is a constant, so p is equal to c into e to the power minus eta square. So, finally, we can substitute for p and we can integrate such that we will get f. So, f is equal to integral 0 to eta c into e to the power minus eta square d eta c1. So, here now in this equation we have to find the C and C1, we can use the boundary conditions. So, applying the boundary conditions we will get C1 is equal to 1 and hence f is equal to integral 0 to eta C into e to the power eta square d eta plus 1, and now from the mathematics we can get integral 0 to infinity e to the power eta square d eta can be written as root pi by 2 and C is equal to minus 2 root pi. So, finally, we get f is equal to minus 2 by root pi integral 0 to eta e to the power eta square d eta plus 1 and ux is equal to we get u0 into 1 minus error function eta. So, this can be represented with respect to error function. So, where ERF eta is the error function and we can also write ERFC eta, the complementary error function is equal to 1 minus ERF eta. So, that is equal to 2 by root pi integral eta to the power infinity e to the power minus eta square d eta. So, now we can use some tables to get this error function and then we get solution for this in terms of the velocity. So, like this now say this is even a transient problem. So, we have transformed the Navier-Stocks equation and finally we can use some mathematical techniques to get an expression for the velocity. So, further we will be discussing some more cases on the exact solution of the Navier-Stocks equations.